Welcome to the deep dive. We take the source material you send us, boil it down, and give you the key insights, just for you.
Yep.
Today, we're looking at something, well, pretty unique. We've got material connecting college-level math differentiation, integration, that sort of thing.
Right. Calculus.
Calculus, exactly.
Yeah.
Connecting that with broiler chickens,
Yes.
specifically chickens raised on farm-grown feed.
It sounds like a stretch, maybe, but it's not. The specific focus from this material is how you can use calculus derivatives, mainly to estimate protein conversion efficiency in those chickens.
Protein conversion efficiency.
Yeah.
Okay.
So our mission here is to unpack that. Understand how this math tool fits, why it matters, practically. Even if calculus or farming isn't your day job, this is for you, the listener, to grab the core idea fast.
Okay, let's jump in then. So you learn differentiation and integration in math class, rates of change, areas under curves. It often feels pretty abstract, right?
Right.
But the question here is, how does that math help estimate something so biological?
Right.
Like how well a chicken turns its food into actual protein.
Well, the sources really zero in on derivatives for this. The link is seeing efficiency as a rate. Protein conversion is basically about output, how much protein or weight they gain, versus the input, which is the feed they eat.
Ah, okay. So it's not just calculus helps somehow. It's specifically derivatives, measuring rates of change, matching up with measuring efficiency, because efficiency is a rate.
You got it. That's the core idea. The sources talk about tracking things like feed intake against body weight gain. Sometimes they use feed conversion ratio, FCR, though that's kind of the inverse feed per unit of gain.
Right.
But the point is, both the chicken's weight and how much feed it's eaten are changing constantly as it grows, continuously.
Okay, now I see the calculus angle.
Yeah.
Because things are changing over time. It's not static.
Exactly. So if you look at the rate the chicken is gaining weight and the rate it's eating feed right at a specific moment, you can estimate how efficiently it's doing that conversion, again, at that moment. And measuring that instantaneous rate of change, that's literally what a derivative does. The source material uses real data bird weight, feed eaten tracked over weeks.
Ah, so you could, like, graph the weight gain, graph the feed intake, and then use derivatives to look at the slopes of those graphs at different points.
That's basically it. You apply differentiation to functions that model or at least approximate that growth in consumption, and that gives you a picture of efficiency across the whole growth period.
And that tells you useful stuff.
Oh, absolutely. Like, when is the bird most efficient? Does the efficiency suddenly drop off? Maybe that means there's a health issue, or perhaps the feed mix isn't quite right anymore.
Wow, okay, that's where it gets really practical. Suddenly this abstract math is giving farmers, like, actual feedback to potentially tweak feed, cut costs, maybe even spot health problems sooner. Huge impact on yield.
Exactly. It turns calculus from a textbook concept into a tool for real-world optimization, measurable improvements on the farm.
So it really underlines how these, rate of change ideas from math class can apply to optimizing really complex biological systems.
Precisely. And the sources are clear. It's derivatives specifically being used for these efficiency estimates, which are vital for making good decisions.
So for you listening, what's the takeaway? It's that even math that seems really abstract, like differentiation, finds its way into, well, unexpected corners. This deep dive shows it can be a really sharp tool for very specific jobs, like estimating and improving protein conversion in broiler chickens. Pretty amazing, really.
It really is. And it makes you to think, doesn't it? Here's something for you to ponder, building on this. If calculus, looking at these rates of change, helps optimize something like chicken farming,
Yeah.
where else could it be hiding? What other complex systems, things that change continuously, could we understand better or make more efficient by applying this kind of mathematical thinking?
Definitely something to think about. We hope this quick look at calculus and chickens gave you some food for thought.